We are back. Let's get this party started. Once again, we will be finishing up our shit on sign tests. We hope to finish T1, T2, T3 by tomorrow night. 2021 T2, T3 by Wednesday night. And Thursday morning, sorry. So 6 papers in 4 days. Come on. If it's not me and Terry, who will? The fuck? Okay. Let's finish the lectures up. And then I'll ChatGPT and Com11 it. Algebra. Binomial distributions in the sign test.
We'll have a look at two very specific.
Okay, we finished this one.
Now, if we there's intuitively just like an event that probability is 0.5%.
Okay, we're gonna finish the sign test now. Disappointed with his previous archery performance, Legolas studies the bows and arrow help manual. Gandalf.
We turn now to using the above mathematics to start making decisions about things. So to decide whether or not we believe a particular hypothesis is true. And there's a number of different ways of doing this, and we'll try and do this just by example. So we'll just have a look at a couple of different examples that we can run, different ways that we can test whether or not someone is telling us the truth. Let us return to the previous example. So we'll return to the previous example. And Legolas has been practicing, and he now claims that his probability of hitting an orc has risen from 1/4 to 1/2. So you'll remember that in the previous example, he had a 25% chance of success. Legolas is now claiming that he has a 50% chance. And you can see it's a bit of a ticklish situation because no matter what the probability of success is, anything can happen. You can have a 1 in 100 chance of hitting something, and you can shoot 1,000 times and you can hit them all. It's incredibly unlikely, but it could happen. So you can see that this whole theory is muddied by the prospect that anything can happen. No matter what your chance of success, no matter how many times you shoot, literally any event is possible. So it's a little bit hard to know when to say, well, that's just too ridiculous. I just don't believe that anymore. Anyway, this is Legolas's claim. He reckons he can now hit an orc half the time. 50% chance of hitting an orc. Now, Gandalf is doubtful, and he runs a test. And in that test, Legolas only manages to hit 2 orcs out of 10. So he shoots 10 times and only manages to hit 2 orcs. Now, immediately, that's not looking too good, is it? Because if he really had a 50% chance, then most likely he'd shoot 5 out of 10. So 2 out of 10 seems a bit low. But we would like to have something a little bit more solid.
More concrete, more quantifiable.
It seems a bit low. We actually need to attach a number to this situation. Okay, so where are we? We've got the probability of a hit being 0.5. What we're going to do is we're going to assume that what Legolas is saying is true.
So let's assume the hypothesis
is true, and we'll calculate a probability of observing what happened under that assumption. We'll see how unlikely it would be to observe that. So let's assume that the probability is a half, and let's let X be the number of orcs he actually manages to shoot. We want to find the probability that X is less than or equal to 2. In other words, we want to find the probability of such a bad observed performance, or even worse. What is the probability of seeing something this bad or worse? So we're after the probability that X is less than or equal to 2. Now that is the probability of 0, 1, or 2. There's the probability of 0 hits. There's the probability of 1 hit. 1 hit, 9 misses, mixed out of 10. 2 hits, 8 misses, mixed. So there is the probability that X is less than or equal to 2. And you can see it turns out to be around about 0.54 on the calculator. And you really do need to calculate it, or else you can't see how big a number it in fact is.
That's right, I'll mute.
Now what that means is this. It means that if Legolas was telling the truth, if it is indeed true that he has a 50-50 shot of success, then we would have observed his performance. The probability of that observation would be 5.4%, which is not out of the question. It is possible. And now we have to make a decision, well, how bad is bad for us? And in this course, we often go for 5%. In other words, if you find yourself in the bottom 5% of the distribution or in the top 5% of the distribution, we would probably start to have doubts about what's being said. Now you can see here, if we have a look at the distribution, Legolas is way down there, 5.4%. That's where he's actually managed to run his test. If it was a little bit less than that, if it was a little bit worse than that, we'd probably reject the claim. But because it just sneaks in, it's just above the 5% barrier, Gandalf would kind of have to accept that, well, maybe it's true. Maybe it is true. Maybe he just had a bad day. Maybe he was just unlucky. So because he was to the right of the 5% barrier, we accept it. If Legolas found his way in here, for example, if you only hit 1 orc, then you start to say, well, that's really just a little bit too small. The probability of me seeing something that you just did is so small that I have doubts that you actually did it. So that's how this test runs. So you assume that what someone is telling you is true. You then calculate the probability of what they have told you happened. And if it is too deep into the tale, you reject what they've told you. Now you may wonder, well, where do you get this 5% from? What made you choose 5%? That's up to you. That depends upon your level of tolerance. So how weird does something have to get before you start having doubts? So for example, if instead of 5% you went to 1%, that would mean that you accept a lot more. You would reject things if they were way, way, way into the tail. So that is a personal choice. It's a personal choice. And certainly it's something that needs to be advertised. You have to say, well, I rejected it because of, and this is my level of significance. That's why I'm rejecting it. Okay, let's have a look at another example. And this is slightly different. So it's quite interesting how we can sort of modify our technique to deal with different scenarios. Fairly simple situation. We have a ceiling system, so something which is meant to seal up a roof or a bathroom or something, so some sort of ceiling system. The previous system had a retention rate of 36. And the new system is expected to be higher. So the previous system was ranked at 36. You're hoping that the new system is better. Doesn't really matter what better means here, what we're measuring. We just hope that the number is bigger. We hope that the numbers are bigger for this new system. And here's the 15 measurements that we make with the new system. And you can see some of them are better, some of them are worse. This one's better, it's bigger than 36. This one's worse, it's less than 36. So judging by this data, judging by these numbers, can we conclude that the new system does give us a higher rating?
Oh, 0
Can
is the
we
one
conclude
that's
that the new system is
gonna
definitely
be
bigger than 36? Now, what we do is quite interesting. What we
0
do
is
is
the
we have a
one
look at
that's
each
exactly
measurement
36.
and we simply write down a plus or a minus. Plus if
Like
it's
it's
better,
above or
minus
it's
if
worse.
it's worse.
Okay.
So you can see the 37.5 goes to a plus, the 35.2 goes to a minus, 37 is better.
I see a lot more pluses than
36
minuses.
is the same, goes to a 0,
Yeah.
etc., etc. So what we end up with is not 15 numbers. We end up with 15 pluses and minuses and a couple of zeros in there as well. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So we end up with 15 pluses, minuses, and zeros. And how many pluses did we get? 11. So there's 11 pluses in there. Now that's a pretty good sign. Intuitively, that's a pretty good sign because it means in 15 of the tests, 11 times it was better. Now maybe that's just luck. Maybe it's luck. Maybe the system is much worse and you just got lucky. But we would now like to assign a number, a value to that observation. How likely is this to see? How likely is that we get 11 pluses or better? So we begin with the assumption that there's no difference. So we assume that there is no difference between the two systems. And what that means, of course, is that we should get half as many pluses as we should minuses. So we would be equally likely to get a plus as a minus, and the probability of a plus would therefore be a half. Okay. So we have.
Okay, so we assume that there's no difference. If it's within the 5% of the right tail end, that means that we're saying X is at least 11. Because we had 11. There's a 3% chance that the old system is the same. So we discard the H0 hypothesis, and the new one is that it is better.
14 differences. We have 14 differences, and 11 of them are positive. 14 differences, and 11 of them are positive. Now, this seems quite promising, doesn't it? It seems as though the new system is better. What is the probability of actually seeing this? What is the probability that x is bigger than or equal to 11, where x is the number of plus signs? Now, let's have a look at what this means. There is your 11 pluses, your 3 minuses, and your mixer. 12 pluses, 2 minuses, mixing the position. 13 pluses, 1 minus, mixing the position. So you can see that all of those are just straight up and down binomial probabilities. That's all they are. What I'm calculating here is the probability of seeing as good as this or better. And the value we get is 0.29, which is around about 3%. Now that is very unlikely. So again, we're operating at a 5% level. And what this is saying is that if these two systems were in fact the same, you would see such a glowing result only 3% of the time. And we're prepared to reject that. So we're prepared to say, look, that is just too far into the tail, and therefore I do not accept this claim. I really do think that the new system is better, because I wouldn't have seen this many pluses unless it was in fact better. So this would provide strong evidence that the mean retention rate for the new system is actually greater than 36. Does it prove anything? No. You can't prove anything here. You can't prove anything at all. You can just lean a particular way or another particular way. This is, of course, the problem with probability, that even if the new system was completely lousy, it is possible that you'll get 11 pluses. Maybe you just happen to get a little bit lucky. Whenever there's probability involved, you really have to be careful of your words. And you can see, whenever you see statisticians talking, they always say things like strong evidence, or they don't say proof. Nothing proves anything. But certainly this would provide strong evidence that the mean retention rate was larger than 36. Let's do another one, paired sign test. And this involves situations where you're trying to compare two things. And this runs along very similar lines. So the table below shows hours of relief provided by 2 drugs for 12 patients. So we've got 12 patients here. We gave them drug A, drug B, and we measured how much relief there was, or how long the pain relief was for each of the drugs suffering from arthritis. Is there any evidence that one drug provides longer relief than the other? Is there any evidence that one drug is better than the other? Well, let's just have a look here. So this is the number of hours for each drug for each person. And all we do is we calculate B minus A and make it plus or minus. So you can see here for this first one, it looks as though B is bigger than A, or B is bigger than A. So it looks as though B is better. Here it looks as though B is better. Here it looks as though B is better. Here, unfortunately, B is worse. So we get a plus if B is doing a better job, and a minus if B is doing a worse job.
So out of 12 cases, once again, there is 9 cases where B does better. If it's 0, does it mean that... Let's read it. If there was 0, this is how many tests? 15 tests, with n being 14. So not 15. Discard the 0. So this is 12 tests with 9 pluses. And so we'd want to see, we'll make a hypothesis that drug B is the same as drug A with 5% significance, and then we'll see if it fits within the 5%. So, is it being at least 9 going to be significant?
And you can see that we end up with a whole batch of pluses and minuses again. So how many pluses do we have? 3, 4, 5, 6, 7, 8, 9. 9 out of 12. Now, once again, that seems pretty promising. So the fact that 9 times out of 12, B was better than A, kind of makes us think that probably B is better than A. Probably B is doing a better job for these patients. But we'd like to have some sort of solid mathematics behind that claim as well. Okay, so let's let X be the number of positives. So let's let X be the number of positives. And let's assume that there's no difference. So once again, we make an assumption. Let's assume that the drugs are equally good. How likely would it be for us to observe this experimental result? Now, X is distributed binomially. It's got number of trials as 12, probability of success is a half. In other words, if they were equally likely, if they were equally good drugs, then half the time you get a plus, half the time you get a minus. So you would get a nice balance there if the two drugs were equally effective. Let's calculate the probability of seeing a result like this or better. So you'll remember we had 1, 2, 3, 4, 5, 6, 7, 8, 9. What is the probability of seeing 9 or more? We always go or more so that we actually look at the whole tail. What's the probability of 9 or more pluses here? Now, a little bit of perhaps a little bit more of an explanation here. It's just a little bit brief up there. So let's have a look at what the probability X is bigger than or equal to 9. Well, we have a half to the 9, a half to the 3, 12, choose 9. There is your 9 pluses, your 3 minuses. We also have a half to the 8, sorry, a half to the 10, a half to the 2, 12, choose 10, a half to the 11, a half to the 1, 12, choose 11, and then finally a half to the 12, a half to the 0. It's just a bit deceptive the way these numbers work. So 12, choose 12. And of course, that is equal to, you can see that all of these are a half to the 12. So because the two probabilities are both a half, they're all a half to the 12. And out the front, we get a 12, choose 9, a 12, choose 10, a 12, choose 11, and a 12, choose 12. And that's where this number is coming from. It just looked a little bit funny there, but it is correct. And we end up with 7% there. So we end up with 0.07, which is around 7%. Now, remember what we assumed. We assumed that the drugs were the same. And it turns out that we're not being pushed all that deeply into the tail. So we're only at the 7% level. We're not actually within the 5% boundary. And so we'd probably have to say that we cannot conclude that there is a difference between the two drugs, because what we've seen is not so strange that we would be surprised by what we see. In other words, if the drugs were the same in how effective they were, it's quite possible that you'll see this result. Even if they are the same, it's quite possible that you'll see exactly what you saw. So once again, we haven't quite gotten into the level of impossibility, the 5% level of impossibility. And so just being careful what we say, we would say, well, probably there's no difference between the drugs. We're definitely not saying there is no difference between the drugs. We're just saying that this experiment really can't lead us to believe to make that sort of statement. Okay, that brings us to the end of the discrete random variables. 3 or 4 lectures now on continuous random variables. And what you'll see with continuous random variables is all the same ideas: distributions, expected value, variance, standard deviation, calculation of probabilities, except rather than summations, what we're going to have is calculus, integrals. Because everything has become continuous,
Integrals.
rather than doing sums, we start doing integrals.
Functions.
And that certainly adds an extra layer of complication to the situation. But we'll have a look at continuous random variables in general, and then finish off the course by having a look at the most famous continuous random variable,
The
which is, of
cumulative.
course, the normal distribution.
Oh.
So that's it for the discrete case. I'll see you over in the continuous lecture.
Hmm? Um, let's go. Let's turn some music. Let's see if there's any of those. So this is normal distribution. Okay. Looks like everything that we've learned until now will continue to lead each other on. So if I want to finish all of this, I have to do continuous variables. Sorry, continuous random variables, which is a few hours worth of lectures. I can take it. Or I'll look at 2020 questions. I want to see. Okay, looks like I'm gonna do that. Yep. Looks like I can do that. Yep. Convergence testing. Yep. Differential equations. Yep. Ugh, scary question. Interest rates. Interest rates. Cool. Yep. Hello. Hi.
Không,
Hi.
có nhà đâu không? Bộ phong bì tiệm cái gì? Ê, có ra đường đâu, có sao bộ phong bì tiệm cái gì?
Oh, không, tại trên lười mặc áo. I'm gonna mute, okay? I have a few lectures to watch. Sorry about that.
Cá thầy không đi.
Yes.
We move on now to continuous random variables. And what you'll see is that almost all of the concepts which we've already discussed in a discrete case will have continuous analogs. So concepts of density functions, expected value, variance, standard deviation, all of these carry across quite naturally. The fundamental difference, of course, is that in the discrete case, the random variable can only take on a countable number of values, whereas in the continuous case, there is a range of values which could occur. Generally speaking, discrete random variables are counted. So you might, for example, be counting cars in a parking lot or hairs on a head, whereas continuous random variables tend to be measured. So for example, you might be measuring the height of a giraffe. Now that measurement, depending upon how accurate you wish to be, could pretty much take on infinitely many different values. So the height occurs not so much here or there, it occurs in some sort of continuum. And that's why they're called continuous random variables. Now, essentially what you're going to see is that pretty much everything we did before we're going to do again, except that the process of summation is going to be replaced with the process of integration. And you've kind of already seen that before when you were discussing the Riemann integral and how the Riemann integral was in fact some sort of limiting process of sums of rectangles. And this theory very much mimics, almost is built in fact on that behavior. So hopefully everything that we talk about here will feel somewhat familiar, just a little bit different. Now, the first thing to discuss is, well, what happens to the probability density table? So what happens to the table of probabilities that we have for a discrete random variable? Now, that table of probabilities turns into what is called a PDF, unfortunately, a probability density function. So the probability density function is the central object that we deal with. Every continuous random variable has a probability density function, and in a very real sense, the probability density function defines the random variable. Now, to get a feeling for what a PDF is, and please be aware that PDF has nothing to do with what you normally call a PDF, which is, what is that, a portable document file. This is a very different thing. Now, if we just think of a histogram, so just imagine some sort of discrete random variables with their probabilities all mapped out in a histogram. And just imagine taking that histogram and using more and more columns. So we start to use more and more columns. And what eventually happens, of course, is that eventually, maybe these two should be swapped, I think, it doesn't really matter. Eventually the histogram begins to look like a curve. So you can see that the histogram, as you take more and more columns, starts to have the look of a curve. And that curve is what we call a probability density function. So a nice way of viewing a PDF is it's like a smooth version of a histogram. It's like a histogram which has become so fine that you no longer see the columns. And in fact, you're looking at a smooth curve. Now, just to get a bit of a feeling for how these PDFs operate, suppose that the random variable X is the age of a group of people. So X is just measuring age. And we can measure that to whatever level of accuracy we wish, to the nearest year, to the nearest month, to the nearest day. if you really want to the nearest second. Let's draw some possible histograms, some possible PDFs. And then let's assume, first of all, that X is drawn from the university. Now, the sort of PDF you'd get there, of course, is one with a huge hump around about 19, but also maybe a slightly smaller hump later on, maybe around 40. And of course, these are the students, and this is the staff. And what you can see here is that the PDF is trying to give you a picture of the population. So a PDF for this sort of situation, we have the main body of students existing around about 19 years of age. And of course, they would represent the bulk of the population. But also, of course, we have the academic staff and the professional staff that would also be part of the mix. Now, if you went to a primary school, of course, you'd give a very different PDF. So if you went to a primary school, gee, what would that be? Around 9? And that would probably be still around 40. And again, the first hump is the students. So the first hump would represent the students. And the second hump would be the teachers. What about an old age home? Well, probably
People in the 40s somewhere, the caretakers, and then the
something like that.
75,
Well,
80.
that might be 80.
Yeah.
And that
30,
might be
35.
30.
Yeah.
And of course, what's happening there is that so here, this is of course X. So what's happening here is that the bulk of the population is quite old. So you're in an old age home, everyone's pretty old. And of course,
Hi.
How many lecture you need to watch?
I need to watch 1, 2, 3, 4, 5. 5 lectures.
You know, I got one lecture, only 1 hour, but keep promising myself from Monday to last week.
To watch it?
Sunday I haven't watched it.
Gotta watch it now. Watch it now.
Tomorrow's the second one, but I will watch the first one.
So
Can
what?
I ask you something?
Yes, babe.
you still have the supporting staff. And then finally, your year 12 class, very interesting, well, that's around 17, isn't it? Almost everybody is the same age there. So almost the entire cohort would be around about 17, 18 years old. Now, what's interesting here is that all of these are X. You're only looking at age. So the random variable X is only examining the age of a population. But the graph, which is attached to X, the PDF, the probability density function, varies with the population. So what the PDF is designed to do is to give you a feeling for the population. Where are the people? Where is the bulk of the people? What's the oldest age group? What's the youngest age group? All of that information is subtly buried within the probability density function. Now let's have a look at a slightly more formal definition. So a probability density function is just a function. So it's a function f. Very important that you appreciate that it doesn't need to be continuous, it doesn't need to be differentiable. So there's certainly no need for this function to be particularly well behaved. It certainly doesn't need to have differentiability and continuity properties, and many PDFs are not continuous. There's really only two conditions that we need. First of all, that the function has to be positive, and that should come as no great surprise. You don't have histograms creeping below the x-axis. So the graph has to be above the x-axis. And the second condition is much more subtle. What it says is that the total area under the curve needs to be 1. So a typical PDF will look like this. And what we demand is that that area is equal to 1. That's what we demand. Now, in some sense, that area represents the unit of population. It represents 100% of the people. And you'll see immediately that we use that. If you're interested in the probability that X lies between A and B, so if you have a PDF and you're interested in the probability that X lies between two values, all we do is we pick off the area underneath the PDF between those two values. So the probability that X lies between A and B is quite simply the integral from A to B f of x dx. That's all it is. And you can see that this kind of makes sense now because the total area is 1. And in a very real sense, that represents the total probability. That's the total probability of everything happening. And once you start carving out subsets of that region, your numbers start to, of course, slide below 1. So once you start to pick off bits of the random variable, so once you suddenly are interested between A and B, you will produce a region. That region will have an area, and that area, of course, will naturally be bigger than 0 and less than 1. Bigger than 0 because the function is above the x-axis, and less than 1 quite simply because there is only one unit of area available to you, and you're picking off a subset of that. So that's essentially what we're doing here. So in summary, what is the probability density function, PDF, of a random variable x? It's just a function. Let me make a discontinuous here just to make a point. So it's just a function. Has to be above the x-axis. And the total area has to equal 1. And whether it's continuous, whether it's not continuous is neither here nor there. It's not something that we really worry about. Now let's have a look at a whole batch of questions that can be asked on this topic. And you have to be a little bit careful because there's a few little tricky things that happen. And just be aware that there will be a fair bit of integration here. Now, I won't do all of these integrals because most of the integrals are quite standard. So it's just TDS integration. But certainly initially, at least, I'll just do a little bit of integration to give you a bit of a feeling for what's going on. Okay, so we have a continuous random variable, capital X. We are given its probability density function. There it is. That is the probability density function. It's x cubed on 64 from 0 to 4. Now you know what the x cubed function looks like. Goes down and then down again. So that's what y equals x cubed looks like. We're not interested in this bit of it. So we're not interested in that. And indeed, we're assuming that it stops at 4. So the actual function looks like this, where that stops at 4. And the rest of it is 0. So just be aware that there's 0 there and 0 there. Just lost the x-axis there. Okay. Now immediately you can see that this PDF is not continuous. Definitely not continuous, and that's no great concern. So that's not something we worry about. It doesn't have to be continuous. Okay, so there's the sketch of the PDF. And just be aware that this PDF has as its domain the whole real line. So it is defined everywhere, every real x. However, most of the times it's 0. So it's certainly 0 here and 0 here. It only has a bit of an interesting existence between 0 and 4. And I should also stress, we'll see this in a second, it doesn't really matter which dots are open and which dots are closed. It doesn't really have much of an impact on us. Now you can see here that it does include both endpoints. So I have gone to the trouble of including both endpoints, but you'll see in a second that that doesn't really matter. Okay, verify that this is a PDF. There's only 2 things that we need to check. The first thing is that f is clearly bigger than or equal to 0. That's obvious. And the second thing, a little bit more subtle, we need to look at the integral from negative infinity to positive infinity of f of x dx. In other words, we need to look at the total area underneath the curve. Now this immediately collapses into an integral from 0 to 4, because that's the only place the function is non-zero. And what is f of x then? X cubed on 64. Now, let me scroll here. Indeed, it does. Okay, so there's checking. And keep in mind that PDFs do not have to do anything fancy. They have to be non-zero, sorry, they have to be non-negative, and the total area under the curve has to be 1. Apart from that, they can do whatever they like. Now, let's have a look at C. find the probability that x is between 0 and 1. This is by definition the integral from 0 to 1 underneath the PDF. This is x to the 4 over 256, running from 0 to 1. That's just standard integration theory. That is 1 over 256. Easy. Now, in terms of a picture, what we're picking up here is a very sad little bit of area there. That's what we're finding here.
Why?
So we're just finding that sad little chunk of area. So it's the area underneath the PDF from 0.
Sorry?
Bago po ba tayo?
Tại sao vậy? Đi ngủ hả?
Cause yeah,
Okay, can I see you? Can you bật cam, please?
and I
over 1. And you can see it's a very small bit of area, but it is non-zero, so it does have some significance. Now, keep in mind that this is how we find probabilities. So don't start drawing tree diagrams, don't start creating sample spaces or grids. None of that is used here. If you want to extract a probability from a PDF for a continuous random variable, you simply need to evaluate an appropriate integral. That's it. There's no other work that is done. So it's just a question of knocking off the integral that you need. Now comes a slightly ticklish problem, and students struggle to get a hold of this, but it's very very important. What is the probability that x equals 1? Well, that is the probability that x is between 1 and 1, which is integral from 1 to 1 underneath the PDF, and that is 0. Now, this is something to get used to. If you have a continuous random variable, the probability that your continuous random variable takes on any value is 0. Because quite simply, there is no area attached to that value. How much area is there above 1? Well, there's none. It's a line. There's no area. So the probability that a continuous random variable takes on a particular value is 0. Now, this takes a bit of getting used to, because what this means is that the probability that x is any number between 1 and 4, between 0 and 4, is 0. And yet, if you want the probability that x is between two limits, it is suddenly non-zero. But that's the way continuity operates. So a region is essentially an accumulation of lines, if you want to think of it that way. The lines have no area, but the region does. And that's just a little bit mysterious, but it is true. Now, the other question here as well, and this is an immediate consequence of what we just said, what is the probability that x strictly lies between 0 and 1? Now, if you just give this some thought, those two have to be the same, don't they? Because we've just seen that a particular value has no mass attached to it. It has no area attached to it. So whether or not you include 1 or you don't include 1 is of no great consequence. So you can actually just let that slide. You don't have to worry too much about it. So indeed, that will be the same, won't it? So that'll be 1/256 as well. Now, there are certainly plenty of situations in mathematics where you really have to need to worry about the endpoints. And certainly in the discrete case, you do. So in the discrete case, you really have to say, well, is this less than 2 or is this less than or equal to 2? And most of the times you'll get different answers depending upon what you do. But continuous random variables don't care. They don't care what happens at the endpoints. You include it, you don't include it, it's neither here nor there. Now, the last little question here, F, probability that x is bigger than or equal to 3, that will be the integral from 3 to infinity underneath the PDF. Now, this PDF unfortunately stops at 4, so we can actually just convert this to an integral from 3 to 4. Now, I should stress that occasionally you do end up doing improper integrals here, so it is not out of the question that this integral will go all the way to infinity. But in this particular case, it doesn't. So it stops at 4, and that is x cubed on 64, isn't it? And so this becomes x to the 4 on 256, running from 3 to 4. This is 3 to the 4 on 256 minus, sorry, wrong way around, 4 to the 4 on 256 minus 3 to the 4 on 256, which hopefully will be 175 over 256. What have we got there? We've got 256 minus 81, don't we? 176. 256 looks right, yes. Okay, a couple of points to just take home from this. First of all of these probabilities come from integrals, all of them. And the integrals themselves are not tough. It's just a question of doing them. So I won't do that many more today. I'll leave you to knock these off for homework. But all of these integrals are effectively year 11 integrals. You just have to remember what it is that you're doing and how these integrals are in fact used to extract probabilities. Now let's have a look at just a slightly more complicated question. A continuous random variable x has a negative exponential density function. So this is just a name, it's a particular name, and this is the graph. K to the minus 2x, x bigger than or equal to 0, 0 otherwise. Now, I have to be a little bit careful here because this one does go forever. So it's the decaying exponential function. So it's a decaying exponential function. Now, over here it's 0. So it stops, starts up again, and it's 0 from that point on. So that's what the PDF looks like. Now, this often happens. There's a K loitering in the definition that we're not 100% sure about, and we're going to have to actually find that K. Now, in fact, when x is 0, y is k, isn't it? So when x is 0, y is k, vertical axis is k. We're going to have to choose k so that this area is 1. Now you can see that depending upon your k, there will be a certain area there. The region will have a certain area. You're going to have to very carefully choose your value of k so that that total area is 1. Now keep in mind for PDFs, only 2 things. They have to be bigger than or equal to minus minus a half e to the minus 0. Examining the theory of improper integral e to the a half e to the minus 0. That's 0. So this is just a half. Cheeky here. I haven't really done this as an improper integral. So if you really wanted to do this formally, you could, and I think we taught you to do this earlier in the year. So you could write this as the limit as n goes to infinity, integral from 0 to n e to the minus 2x dx. So if you really want to do it formally, you can express it as a limit, do the usual things we do in improper integrals. But here we're not really examining the theory of improper integrals. We're just trying to find a value of k. So all I've done there is, well, I've just treated infinity as if it were a number, which it isn't. You put in the upper limit, you put in the lower limit. E to the minus infinity is 1 over e to the infinity, which is clearly 0. It's 1 over something huge. And of course, e to the 0 is 1. So we immediately get a half. Therefore, what have we got? We've got k times a half is 1, and therefore k has to be 2. K on 2 is 1, k is 2. Okay, that's easy. Now what that means is that it is only for that value of k that this is a PDF. It's only for that value of k that the total area under the curve is equal to 1. Probably the x is between 3 and 4. Now, about point that x equals curve is pretty close to the x-axis by then. So the curve is pretty much dropped down to the x-axis by that stage. Easy. Last little question here, always a trick question that we ask. The answer is always 0. So the last little question here, what's the probability that x equals 4? How much area is there above 4? None. Probability that x equals 4 is 0. Lovely. And that's pretty much always true. It's always true. A continuous random, the probability that a continuous random variable takes on one of its values is always 0. Now, we have two associated concepts here which you're already familiar with. The idea of expected value and the idea of variance. Now, the definitions mimic the definitions we've already seen. The expected value, you integrate x against the PDF. You will remember in the discrete case, we summed KPK, K times PK. So this is like KPK. It's essentially the same idea. And that's our formula for expected value. Now, variance, again, we have an integral, the distance between x and its mean squared to make it positive, multiplied by f of x to multiply by its significance. So that's the concept of variance. And we also have the proof that I gave you before still works, that this is the same as e of x squared minus e of x all squared. So we have two different ways of evaluating variance. Now, the meaning of these two is still pretty much the same, but let's just revisit this. If we have a PDF, so if we have a PDF, where is the expected value? If you imagine the PDF being made out of wood, so just imagine that this object is made out of plywood, the expected value is where you'd put your finger to balance it. It's the point of balance of the PDF. So it is often still a measure of center, isn't it? Now, those of you that study physics, I think will recognize this formula as being the formula for center of mass. And that's what it is. The expected value is the center of mass of the object. So it's where you'd place your finger underneath the PDF to balance the PDF on your finger. It is the center of mass of that object. And what variance measures, of course, variance measures, so this is still a measure of center. And this, as usual, is a measure of spread. Now, what that means is if your PDF looks like this, it has a big variance because the people are all over the place. Whereas if a PDF looks like this, you have a very small variance because everyone is roughly the same. So if your random variable is really tightly batched around your mean, you have a small variance. If you have people all over the place, if your random variable is measuring height, for example, if you have lots of short people and lots of tall people, then you have a large variance. Now, that's pretty easy to remember because the word variance comes, of course, from vary. It's how much your random variable varies, the degree of variance. Now let's have a look at some of these calculations. Now you can see that both of these calculations are just integrals. So they're not hard to do, but they are tedious. And I will leave some of these for homework, I think, because really it's just simple integration theory. Okay, lovely little example. Let's do example 4. We have a continuous random variable
I want to be able to use the PDF function and find the mean of said function on Maple. So I want to define the function with the statistics package. Then I do want to understand how, like, we could find the. I mean, I'm gonna find the domain to make sure that the function evaluates, the integral evaluates to 1 over the domain. But then how do I write it so that I can find certain things with the statistics package? Nice.
Complex. There is its PDF, probability density function. You can see again, we haven't got a K up here like we did before. We now have a K down there. So we still have to try and work out what K is. So we're going to have to try and work out what K is. And it's 0 otherwise. So O dot W in stats always means otherwise. So this always means, it's not something we use a lot apart from here. So that's otherwise. Okay, so let's have a look at some of these examples. First one, sketch the function. Now this is pretty easy. It's just a parabola, isn't it? So just a parabola, x squared on 63.
A little fat parabola.
It stops. Where does it
So
stop?
he
At
has to,
K.
he has to
I'm not
do
sure
it
where
at
K
3,
is.
so he should delete some
And it
of
stops
it.
at K, and then starts up again over here, and also starts up again over here. And it's a parabola. Okay, so that's our object. So there's the sketch. Isn't it? We now know of where all the map deviation. Well, 10 really do is area.
Suppose that x is a continuous random variable with the population density function f, and the expected value mu is equal to mean. Is it true that most of the area under f is concentrated near mu? We don't know. I would not know if that's true or not. And find the probability that x less than mu is a half. If it's continuous, right? It doesn't matter.
Area is constant. We'll say that's 2 and that's 10.
Yeah.
The expected value of this PDF would be round about
7, not 5.
would be round about 6.
Oh yeah.
And you can see that round about 6, there is no one. There is no one. So you have to be a little bit careful how you interpret the expected value. You can see that if you're going to balance this object, this is where you'd put your finger. That's where you'd put your finger to balance it. But that doesn't mean that there's a lot of people there. So if half your population takes on a value of 2, and the other half of your population takes on a value of 6, sorry, a value of 10, then the expected value will be around 6, even though there's no one there. So you just have to be a little bit careful how you think about the expected value. And the second question, also the answer is no. Is it true that half of the area lies to the left of the mean? And the way to think about this one, just imagine a PDF that's like this. So there's a little bit of area there and a little bit of area there. Now, where would the expected value be here?
Leaning a little bit closer to here, maybe.
It would be round about there.
Yeah.
Once
that-
again, think of it in
that
terms
has
of
like
balance.
80%.
Where would you balance this object? Where is the center of mass? And you can see just by virtue of a lever, if you like, if you want to think of this as a lever, although there's not much area here, because it's so far out, it actually has quite a bit of impact. So because it's living so far away, it actually tends to skew things a little bit. And you can see here that most of the expected value most of the area is to the left of the expected value. I suppose this question is a little bit like this. Is it true that in a population, say you've got 1,000 people and you measure their height, is it true that half of the people are underneath the average height? And the answer is no, because you might have one or two really tall people that skew things away. So that's the idea here. So just be a little bit careful how you think of the expected value. It's a fairly subtle sort of concept. Those of you that are coming to this with a bit of physics, it is center of mass. You can think of it as center of mass of a rod of variable density. But just think of it in terms of where would you balance things? Where is the point of balance? Now, just a few last tiny little things. We've seen this before. You will remember that the expected value of AX plus B is AE of X plus B. That's still true for continuous random variables. You'll also remember that the variance of AX plus B is A squared variance of X. That's also true for continuous random variables. So those sorts of facts cut right across continuity and discreteness. They apply to all random variables. And the last little thing, which I've already used, is that the expected value of X squared is just integrating X squared against the PDF. If you want the expected value of a function of X, you integrate that function of X against the PDF. And we've kind of already seen that. Now, hopefully that was quite comfortable, because really the ideas are not new. So I think you've seen most of these concepts before. There's nothing really hard in this lecture, I think, apart from all the integration theory, which is not that hard. So it's just tedious. You just have to do the integrals. It's not that difficult. Anyway, that brings us to the end of this initial topic on continuous random variables. Now, there is, of course, one continuous random variable which is more famous than all the other ones put together, and that is the standard normal distribution. And what we'll do for the remainder of this course is have a good look at the standard normal distribution, discuss why it's so important, and how we go about extracting probabilities from the standard normal curve.
Are we in trouble? They've got we dominate. The flop, ace, queen. The turn, another ace. He can only chop now. The river, king. They make a full house, but we have a bigger full house. Then there were three. Ace five, all in. He calls 8-3. 5 on the flop, ace on the turn. We're heads up. Can we finish the job? Follow so you don't miss out. Win the button final table. 4 left, 14.
Give me your shirt. I will do that. No, don't give it to me. That would go viral. If you give me your shirt. I don't want you to go viral, buddy. I'm trying to get out of here. Give me that little lady. I will do that. I need to work everything at WSOP. Okay, it's good. Nothing happened. Where is Rampage? Rampage, apologize to the spectators. Okay. Now, like new. Everything like new.
Yo, this is the noodle.
Generate.
Now, what's interesting is I've been saying, look, if you want probabilities, you just find area, you just integrate. Now, unfortunately, the standard normal curve has an equation which is essentially e to the minus x squared. And what that means somewhat remarkably is it can't be integrated. We know that we need to integrate it, but the integration integrate it. We know that we need to integrate it, but the integration won't go. You won't be able to integrate it. And what this means is that when we're dealing with the standard normal curve, either we use a computer or we use a table of probabilities, for the simple reason that we can't actually run the integrals. It's not often that we strike an integral that we can't do, that we really want to do, but certainly the standard normal curve is an example of that. Okay, next lecture. First of all, the standard normal curve, and then we'll have a look at generalizations of the standard normal curve. Two issues that we'd like to have a look at in this lecture. First of all, the idea of a cumulative distribution function, which is very closely connected with that of a probability density function. And then we'll move on to the most famous of all continuous random variables, which is the standard normal distribution. But first of all, the cumulative distribution function. Now, you will remember from the last lecture that for a continuous random variable x, we talk about its PDF, its probability density function, which is essentially like a continuous histogram. It's an attempt to get a feeling for where the population lies. And these functions, these PDFs, really only have to have two properties. They have to be non-negative, and the total area underneath the curve has to be 1. And it's important to appreciate that nothing else is required. They certainly don't have to be continuous or differentiable. They really are the only two conditions that we demand. So what they are is essentially just some sort of curve, and all of that area, the area of the region underneath the curve, has to equal 1. We can then extract from that probabilities, and the probability that x lies between A and B is quite simply the area underneath the PDF from A to B. So if you're interested in the probability that x is within that range, all you have to do is to find that area. And of course, you know that the total area is 1. The total area is 1. So this probability will definitely be bigger than or equal to 0 and less than or equal to 1, as you would expect. Now, if we start with that situation, so if we start with a random variable x together with its probability density function little f, we can create a new function, which we call the cumulative distribution function. And interestingly, it's almost always denoted with the capital. So if the PDF was little, G, the cumulative distribution function would be called capital G. So we usually just go uppercase because the two functions are so closely connected. And the definition of capital F of x is very, very simple. Capital F of x is quite simply the probability that x is less than or equal to little x, which is the integral from negative infinity to x underneath the PDF. So it's important to keep all of these things straight because there's a lot of action here. So here's little f, here's a number x. If you evaluate capital F at x, it simply looks left from x. It measures the area to the left of x. So capital F of x, the cumulative distribution function, and of course what it does is it accumulates the area. So as you move your x from left to right, capital F is quite simply accumulating the area underneath the probability density function. So capital F at x is the probability that capital X is less than or equal to little x, which is the integral from negative infinity up to x underneath the PDF. Now, just a small point here that does cause a little bit of confusion. We can't use x's here as well. If we have an x in the limit, we certainly can't use x as a variable of integration. And we saw that with the fundamental theorems as well, the fundamental theorems of calculus earlier in your studies, that we had to use a dummy variable. Does it have to be t? No, it could be anything. Could be q, could be r, any variable will do, pretty much as long as it's not x. Then let's have a look at a little example, just to get a bit of a feeling for these objects, because they're quite interesting. So we have a continuous random variable x. This is its probability density function. So it's equal to k if x is between 4 and 10.
So now we have kind of reading said function at different ideas, whereas probability density function is very crude. It's very rigid. It's like I'm going to choose two of these points. I'm going to choose the probability between these points. Cumulative distribution function, like what it says, it accumulates, and it basically measures all of the probability as we continue. So it's a range from the upmost left-hand side to the point X that we are evaluating. So let's just once more before we go anywhere. Tons of shit we learned. Right. K. So A is f of x is k for 4x 10. Right? We integrate k from 4 to 10 such that this is equal to 1 because k is not since k is not something we care about. There you go. We'll just put this here. Then that's equal to x 10 4 k 1 k times 10 minus 4 is equal to 1. 6k is equal to 1. So if only they would have taught the content like quicker. Okay. We have 6k is 1, which implies that k is equal to this. Sorry. Yep. Find PDF for F. Sketch the PDF for F, sorry. So it's a super, it's a flat. It's a flat bitch. Here's my graph. Here's F at, 4 to 10. And this is at 1 over 6. This here is at 1 or some shit. Right. Find and sketch the cumulative distribution function f of x. F of minus infinity to f. That's it? What's the same shit? Same. Find f of x is equal to p of x big X over x is equal to this from this to this of 1 over 6 dt, which is more or less equal to x for 1 over 6 dt. Calculate that p of x is less than 8. The probability of x being less than 8. Which is around here. P of x larger than 5 is equal to 1 over P of x less than 5, and we'll just draw it right here, you know? So at least equal to 5, and this one is 4, 3. One minus 1 minus 5 over 4 minus 1. So it's going to be like
and 0. Now, the interesting situation, of course, is what if x is in between 4 and 10? Well, capital F of x is the integral from negative infinity up to x f of t to t, which is the integral from 4 to x of a sixth to t.
Yeah.
A lot happened there. First of all, there's no point in going all the way from negative infinity because things only start to happen at 4. So we only run the integral from 4. We're essentially assuming here that x is there somewhere. Now, I'll do this using calculus, but we don't really need calculus here. But this is a sixth t running from 4 to x. And this is a sixth x minus a sixth 4, which I'm going to suppose write as x on x on 6 minus 2/3.
Where is he writing this?
Yeah, I'm happy with that.
Oh, is he trying to find
And
the
this
cumulative
gives us our
function?
definition of capital F of x. And you can see it has a very convoluted sort of definition. So it comes in 3 pieces.
Ew, that's how you're gonna do it? The function f, big F of x, is equal to... So maybe I'm wrong? It doesn't just accumulate?
So if I do that properly. So it's equal to, let me just present it in exactly the same way as I did down here. Okay, so it's equal to 0 if x is less than 4. It's x on 6 minus 2/3 if x is between 10 and 4. And it's 1 if x is bigger than 10.
Whoa.
And that's the definition of capital F.
I've never
That
thought
is
of it
the
like that.
cumulative distribution function. Let's draw a picture of this.
Oh my god.
Now, again, we have action from 4 to 10, don't we? That's where things are happening. I might actually try and use a different color here. So
No, I would assume
let
that
me use red.
what we were
So
doing,
it's
the stuff that we
0 to the
calculated was
left of
fine.
4. Just find appears up as a strong action. Is now for that the cumulative.
Valid though.
So on the left-hand side, the cumulative distribution function tends to be 0 because there's not much area to the left. Whereas on the extreme right, it tends to be 1 because all the area has been picked up by them. And it also rises. So as you go from negative infinity to positive infinity, the cumulative distribution function will slowly increase from 0 to 1 because initially there's no area to the left and eventually there is all the area to the left. So there's our cumulative distribution function, capital F of x. Now, and we've sketched it as well. So we found it, we've sketched it. Let's calculate the probability that x is less than or equal to 8. Now, this is quite interesting. If you want the probability that x is less than or equal to 8, you don't need to use the PDF, little f. You may as well use capital F. And capital F at 8, of course. This is a question asking you to look left from 8. This is the job of capital F. So all you have to do is evaluate capital F at 8, which is 8 on 6 minus 2/3, which is 4/3 minus 2/3, which is 2/3. So you can see there that, oh, it's interesting.
That's pretty sick.
So you can see there that it gives you another string in your bow. You don't have to go to the PDF little f. You can go to the cumulative distribution function, particularly if you're interested in looking left. So if you're interested in looking left, that'll do the job for you. Now, even if you're interested in looking right, so what is the probability that x is bigger than or equal to 5, which is our last question here?
So 1
Probability
minus
that
f of x?
is bigger than or equal to.
So this you could also do That's pretty sick.
Cert, not right. But we can argue that this is 1 minus the probability that x is less than 5.
Which is
This is
less
1
than or equal
minus
to.
capital F at 5.
Sick.
This is 1 minus, what is capital F at 5 using our definition? 5 on 6 minus 2/3.
Never thought of it like that
Be
before.
careful here. So that's capital F at 5. 5 on 6 minus 2/3. This is 1 minus 1 on 6. 5, 6 minus 4, 6, which is 5, 6. Looks good. And again, we could kind of guess that. Now, you could have guessed that directly from the PDF. If you go right back to the PDF, you can see that if you want x to be bigger than 5, you're picking up 5/6 of the area quite clearly, 5/6 of 1. So that's how we use the cumulative distribution function. We use it to find probability less than, probability bigger than. And it's a very handy tool for that sort of job. Also, just by the by here, if you put a less than or equal to there as well, it wouldn't be the end of the world. So remember that with continuous random variables, the probability that the random variable takes on any of its values is 0. So you can just be a little bit sloppy when you move those inequalities backwards, but still it's probably best to do them right. So capital F tends to be continuous, even if little f isn't. And we've discussed these issues as we've gone along. So every cumulative distribution function will be increasing because you're picking up area. There's no such.
So the point that it is evaluating is the probability. This one here is 1. Because at x larger than 10, cumulatively already took all points. Very cool.
There's negative area here. So you're always picking up area. So there is always an accumulation of area. The function's always going up. And it'll rise from 0 on the extreme left because there's not much area to the left then, to 1 on the extreme right, because on the right, all the area is already to the left of that point. Now, you would imagine, and this is certainly true, seeing as capital F is the integral of little f, it is certainly true that little f is the derivative of capital F. And of course, this is just the fundamental theorem of calculus, nothing else. So capital F is found from little f via integration. So not surprisingly, little f, the PDF, is found from capital F, the cumulative distribution function, via the process of differentiation. And this really is quite literally what we used to call the first fundamental theorem of calculus. So let's have a look at what happens if we go the other way. And please do be careful that you're aware of what you're being supplied with. So make sure that you're aware about whether you're dealing with a cumulative distribution function or whether you're dealing with a probability density function.
Well, before okay, let's take a look at this question. We'll be drawing the cumulative distribution function. We have 0 right there. We have 3 right here. we know we'll just put that point there as a negative 40, and then it's a graph that kind of, I mean, here, I'll do negative 40 here. It's a quadratic, right? It grows up to 1. How do I do it so like it looks like, I mean, basically it goes to 1, but I'm just gonna give it some size there, and then it's just a straight line at 1, and then this is 7, right? That's what the cumulative distribution function looks like. We're going to delete the this part here. Boom. Basically, it's good enough. Actually, we'll just delete half this fucking joke. Good enough. Find P probability that x is larger than 5, which is same as probability, 1 minus the probability of x being less than 5. Or the integral from, 1 minus the integral from minus infinity to 7, not minus infinity, but 3 to 7 of ooh. Nah, it's just, ooh. See, they say find and sketch the probability density function. So we have to differentiate. Maybe like that. Let's see if it works. Oh my god. Sorry. F of 5. I'm hungry as a motherfucker. I think I'm gonna turn it off because Christine says.
buying it every time.
Music is right.
And I mean, e-com is dead. Products are saturated. It doesn't work when I'm holding one. How to unfuck your life in one easy second. One, two. This is what happens. Hey, get that phone and then tap on it. How much is this on? I've got a question. Do you think your business would benefit from getting more good reviews? Yeah, absolutely. So basically, here we've got our product. Yeah. When customers come in, they get their phone and then tap on it. The one for 50 and then two for 70. You just buy it once and it's legit for a time. Like here. Yeah. Thank you. Hey, get that phone. Fastest way to shut down your digest. I have 3 years left of it. How long does it take the guy? Right, so behind in life, 22 years old. I met $2,000 a month. That's crazy, man. My first thought was just like, wow, that's insane. Like, imagine making that much money at that age. It's gotta be huge. Real. You're suffering from sciatica a lot. Pretty good, Rachel. Oh, hey, man. It's been a while, huh? Yeah, it's been a minute. How you been? Been pretty good. Once you get thrown out of college and you get a job, and all of a sudden you're just like living the corporate life, you reach a point in your 20s where you start to realize like those dreams you had when you were a kid, that those are like going away. Like, and you're not. It just time passes. Now I'm 26. If I ever wanted to go all in, start a business, whatever, now is the time. So this is the argument that I was making to myself. That I quit my job with no backup plan to go all in on this in calisthenics, and but more than that, I wanted to start a business. I wanted to start a business in like a bigger space, the bigger market, and do something that was even bigger vision. That was my plan. I was literally like, I was sitting in this car, in my car, not 10 or 11 days ago, talking about how I was quitting my job and going all in and giving up, well over 6-figure salary and great career path. I was giving all that away to go, to basically take my income close to zero. So like, how in a span of 10 days did I go from like I'm going all in to now I'm going to take this new job? Once you get thrown out of college and you get a job, and all of a sudden you're just like in a if you want what? Yeah, boy. If you
would it be that this is equal to 1 minus 25 over 40 minus 9 over 40 was equal to 1 minus 16 over 40, which is 8 over 20, which is 4 over 10, which is 0.6, or 1 minus that. No, it couldn't be. Could it be? Two x. No, that's not the same.
Now you can see that they're very, very, very different. Going back here, there is the probability density function. There is the cumulative distribution function. They're completely different. So make sure you're aware which one you're in fact playing with. Okay, so let's have a look at this one. A continuous random variable x has a cumulative distribution function, capital F, and we try to help you along by using capitals for the cumulative distribution functions. And this is quite an interesting definition. So it's 0 to the left of 3, a parabola between 3 and 7, and then 1 to the right of 7. Let's have a crack at sketching this, and we can kind of do it intuitively. Whether this is 9 minus 9, you get 0.
Basically.
And when you put 7 into this, you get 49 minus 9, which is 40 on 40, which is 1. So it joins up on both endpoints, which pretty much it has to do because it's accumulating area bit by bit. It can't accumulate a sudden chunk of area. So capital F does tend to be, a continuous object, even though little f isn't. Now you have to be a little bit careful here. So B, probability that x is bigger than 5. This is 1 minus the probability that x is less than 5. This is 1 minus capital F at 5.
Yeah, how do I convert
This
back
is
to
1
probability
minus.
density function?
And what is capital?
You know how PDF is PDF is some F 0 otherwise. And it's like some function here. And then like CDF is big F. You know?
left at 5, it's in this range here, isn't it? So that's going to be 25 on 40 minus 9 on
Ow.
40. So all on lit on 9.6, for example, there's still a probability, and the probability that x is bigger than 5. Whether the x, that x and are equal to minus.
Yeah, I mean, C is gonna be fine, right?
The area to the left of 4. I can believe that. No drop. I can believe that. Of capital F.
Okay,
No
this is what we
drama.
need.
We just have to.
F is this. Then we have f of x is equal to 0 to x on 40, right? Which is x on 20 for x between 3 and 7. Is that right?
Different. So that's what your PDF looks like. So we're now talking about the PDF. Now, what does that look like? Let's just have a bit of a look at what it looks like.
Some increasing function.
3 and 7.
Right? So it's
There
just...
we go, red again.
Oh, okay. So it's just like that.
Now, interesting. So between 3 and 7 is just a straight line, isn't it? It goes from 3/20th. And you can see that the PDF indeed is not continuous. There's no reason for it to be continuous. Oh no, very, very nice. So there's the PDF extracted from the cumulative distribution function, little f calculated from capital F. Just as a last little check really here, check that this PDF works. So this is not a random function, of course. This has to do all sorts of things for us. So let's run a check. Is f bigger than or equal to 0? Well, that's certainly true. What is the integral from negative infinity to positive infinity f of x dx? Now, if you wanted to, you could actually use the area of a trapezium here, because this area, this region, in fact, is a trapezium, isn't it? But you don't really have to go down to that. 9 on 40 minus 9 on 40, which is 40 on 40, which is
Okay.
1.
Oh, so normal.
Exactly what we wanted. So the total area under the curve. So therefore the total area equals 1, which is exactly what we need. Beautiful. Now, This takes a little bit of getting used to because it is a secondary object, isn't it? So there's another object floating around. This takes a little bit of getting. Now, this takes a little bit of getting used to because it is a secondary object, isn't it? So there's another object floating around now. Which of the two that we see most often? Definitely little f. We tend to be dealing with PDFs much more than with cumulative distribution functions. PDFs are just a little bit handier. They're a little bit easier to use. And in particular, it's nice to be able to calculate the probability that your random variables between two limits just as a single integral, rather than sort of fiddling around with regions to the left of points. But both of them are of value. So capital F is the integral of little f is the derivative of capital F. And just be a little bit careful that you're aware of which one you've been supplied. So these sorts of questions, just really look carefully at the question. Make sure you're aware of whether you're dealing with a PDF or a cumulative distribution function. And also, we tend to alert you in the variables. Lowercase is PDF, uppercase is cumulative. So you'll see it in the variables as well. So there's the general theory of continuous random variables. There is, however, one random variable which is more famous than all of them, which is often referred to as the bell-shaped curve, the standard normal distribution. And the rest of this course, in fact, will be dealing with the standard.
Through the night, side of my heart, it's the sweet of light. In my dark, you're my flashlight. Get me through the night. 'Cause you're my flash. Two more hours of the content. Basically, I'm finishing all math lectures. do it yet. I don't think so. Okay, we can do this question, which is pretty nice. I'm gonna do this question before I make some tuna. Right, so they gave me a PDF, right? Here you go. And that G is continuance about the vertical line, X is minus 45. So what they meant is this is X at minus 4.5. And this function is some function in between here, right? Let's call this 0.6. Oh, let's just scale this fucking motherfucker up. Wrong. The probability that X is, it's a continuous function, symmetric. Symmetric. So say it like this. Right, and the distance from here to here okay. The probability that X is less than 4.5 is the same as the probability that X is larger than 4.5. Yes. Because it is symmetric. Symmetric. So, yes. No. Px is 0. P of x at all values of, let's see, what are they saying? They're saying this function at values of at least larger than 4.5 is larger than values of is larger than of at least the of at least minus 5.5, which is not true. P of x is less than P of x at minus 3.5 and 3, which is like there. Sorry, right there. Is less than 3.5 and 2. That's true. Distance 1.5. Distance 0.5. Boom, boom, boom. This one is larger than that one. Wrong. We just make sure that we got that right. And we can do this question as well. Nice. Is it 29 first? It's this one and this one. Sorry. Oh, equal. Equal. True, ba chấm năm đến 2. Okay. So only this one's right. And this one's right. Some alpha such that, I mean, we want this to be equal to 1, right? So they want us to find some alpha such that this is equal to 1. And if I integrate, I'll pull alpha out, and then I'll just integrate in my mind. I should just integrate it here. I think we'll do like solve the open bracket the x times integral of x. Ooh. We should do k, solve integral of x squared minus 11x plus 28 comma x is equal to 4 to 7, and then that's equal to 1, and then solve for k. K is 2.9. Oh, I've got this down in the bag, bro. I feel it. K times int x squared minus 11x plus 28. X is 4, 7 is equal to 1 of k. K is that. Minus 2 on 9. Here, I'll show that to you guys. Like that right there. Takes like 2 lines of work just to get the answer. And then the expected value of x is equal to x times f of x, right? Then f of x is equal to 2 over 9 times e of x is equal to integral of 4 to 7 of x times, let's do minus 2x over 9 here, times x squared minus 11 plus 28x dx. And then with maple, once again, that is equal to, right now we only need int. So we're gonna have int, but we're also gonna close another bracket into this, and then we'll open bracket again right here, open bracket, minus 2x on 9 times the whole quantity, we have expected value is 11 on 2. Okay, that's basically all we need. I'm gonna copy this right here. Doesn't take much. No bueno, no bueno. Nice. So most problems are, so there's this one that hasn't been solved, Q26. I'll take note of that. Every other question has been solved. Okay. I mean, with this I could pass. 31 is one question. 32. I see a normal distribution, so. And 33. So Q26. Q26. Q32. Q33 left. Okay, I'm gonna make some tuna omelet and then probably eat it. I'm really hungry.
I didn't tell people I owned the business. I told people that I was the manager and everyone was very happy to pay adult prices to someone capable of working for an adult. And whenever I had to let me see if the boss will do it. I would step outside and I'd pull my phone out and I would just do nothing, and then I'd come back in and be like, yeah, he's good with that. And then I even had a celebration where I'm a part owner, and people were like, oh yeah, he's a part owner. And so that's actually how I managed to do that when I was so use it. Hi Alex, I'm 24 years old and look like a. What stops you from using your wealth to change somebody's life? Nothing. Listen, I live 3 places. I live in Florida, I live in Maui, Hawaii, and I live in
Let's just make sure we got everything we got right. Minus 209. And 11 on 2. Hell yeah. Okay, let's just make sure. Boom, boom, boom. Sick question. Milan Pahor taught me all of this. It's like taught me how to do all of these questions. Anh thật sự yêu em nhưng chỉ là quá khứ thôi. Đừng bạn xin anh đừng đi, bây giờ thì em cứ thử. Có như đã làm gì có. Anh thương em nhiều lắm nhưng em đâu nào hay. Sẽ nhìn mình em với Okay. I'll use Kali High. Cal. How about I just eat the meal for, yeah, I eat the meal for tomorrow.
chick? I sort of love the elf chick. You play this?
I don't fuck with elves, bro.
Elves are funny. Songs are
I don't fuck with elves, bro. Shit was good though.
You read the manga?
Nah, low key considering it.
So that the manga is a lot more interesting process. Yeah.
I know Dana said she would see readings and posting shit. That's what she would tell me. She sees me read some obscene things. Bro.
No.
What were your like favorites that you were watching?
High school DxD. I think maybe it's what Jada saw me once.
Oh, that. What the fuck? About the first fucking Mushoku Sensei definitely.
Yeah, no, it's good. That one's good, but like
Bro, it's up there as in like
the
top
sex
thing.
and shit.
Yeah, like top things worse than not watching.
Yeah, no, it's bad.
No, it's
Rudy
people always be peeking at your stream when it's like some fuck shit.
Rudy has
No, like
underwear, bro.
I watched Naruto next to her, bro. I watched Naruto next to her. Yo, she was so calm the whole time, bro.
Yeah.
So calm, bro. He was fighting shit, bro. She looks over that. And of course, that's when he decides to pop the hair juice. That's when he decides to pop it, bro. Like,
GG, bro.
dude, like, what the fuck?
That's so dumb. Oh, bro. Come on. Mr. God, I'm telling you to stop watching it. So we should be an anime character.
So,
Being an anime character or something, bro. Oh, there's this like smartphone anime. I watched it the other day. You know? It's like isekai. The guy fucking he isekai, but he had his phone, so he could search up shit. You search up like smartphone isekai, so like things.
I ain't heard that. I thought you were talking about ReZero for a second.
No. Zero? Yes. Wait, there's another anime that's similar to ReZero.
Or like, it's isekai.
Yeah, it's another isekai, but like the guy dies and respawns, and he sees his ex or some shit, or his ex-wife. Exactly. Exactly. No, okay. Okay, Attack on Titan event.
Oh, bro, you know I got her to watch 7 minutes of Attack on Titan.
And what you say about it?
That's because she wasn't into it, bro.
Yeah. Dude,
Bro, Attack on Titan arguably has the best first episode ever.
is that the Walter episode?
Yeah, literally the first episode, the fucking whole city gets jumped.
Oh yeah. Armor Titan.
Yes, bro.
And it's all in. No, it's over. I would grind it again. Wait, how do you how do your grades and courses transfer?
You said how?
Yeah, is it just like you
I
get
gotta
the
submit.
credits?
I gotta submit my transcripts, and I gotta submit all the syllabus.
Did you do that?
Yeah.
Oh, so you're like,
I'm just waiting.
but you're enrolled.
Yeah, I'm fully involved in that. Alright, so let's go back to it.
Power transcript.
Let's go back. Oh, that's my favorite one. It was my first one.
How about Boruto?
If you watch the manga canon,
Wow.
if you watch the manga canon,
I did. story. Oh, so it got shit. But like, if you only watch the episodes where they adapt the manga, it's good. It's a weird, like, yeah, it's like 60%. They fucked it up. It's the parts where they actually the manga. I didn't watch it. Watch it. Yeah, but I saw the fights with who do you think is my favorite character? Ethan. Ethan. Oh, is it? Yeah. Nah, you've heard me say. No, I guess Dad. Ain't no way. No. There's no way. You just what the fuck? Yeah, it's way telepathy. Bro, it's fucking Itachi that fucking predicted. I swear he's not that bad. I would have thought like Kakashi or something. Well, like roughly, bro. I think I like Mike God. Mike God, yeah. He had one moment in the whole show. Oh, that's the sickest moment ever. Yeah. So about that. In that like, what is it, 7th form, 8th form? He would probably shit on everyone. Then he dies. You have to die. But unless you have Naruto. Naruto, then I should give him a heart. The other one, Gaara. Oh, Gaara. I've heard Gaara before. When Kakashi valid, it's just he becomes kind of like once Naruto becomes stronger than him, he just stops becoming cool. Yeah. Yeah, like he or like I just stopped finding once Naruto's baby. Oh, like you don't like Naruto? Okay. I mean, he's just really corny. I don't like it. He's just like the corniest main character, like the most typical, like. Yeah. I love you. Was that the Veil? Fucking bullshit. You seen Vinland Saga? Huh? Seen Vinland Saga? Vinland Saga? Yeah. I actually think it's one of my favorite animes. Even season 2? Yeah. You don't like it? Nah, because a lot of people like that don't really watch, like they don't really like care about the story that much. They just watch it for the fights, so they say some shit. I think season 2 was a lot more about peace. I enjoyed watching it. Oh, dude, like I just recently finished My Hero. Gas? Bro, it's like the conclusion of the story. Bro, the fandom is weird as shit. That's why people give it a bad rap. But if you just watch the fucking show, good show. I didn't watch season 5. Can you tell me? And they won. Won against the villain? They beat like all the villain shit. But then fucking Neptune's season 5. And then he has a scar, right? Wait, you said you didn't watch season 5? Yeah. There's 8 seasons. Oh shit. Never mind. No, I'm real bad. There's a movie. Yeah, but none of the movies are relevant. Oh, then I don't know the fine. I'll show you some JK. JK. I didn't finish it. Wait. I know you've had a romance anime. Everyone has romance. You know what? It's a sexual. What? Was it? Bro, the ending had me pissed for a week. Miku. Itsuki the horn? No, the horn is Yotsuba. Oh, Yotsuba. Ichika's like who's the short hair one? Ichika? No. Well, Ichika's the short hair one. Yotsuba's the orange hair one. Itsuki's the first one he meets. Itsuki's the pink, purple. The one with the star. Yeah. And Miku's the shy one, and Miho's the studio. Fucking bro. I love studios. Fucking love studios. What happened to the final? You fucking picked picked Yotsuba.
Oh, really?
That's why I was pissed for a week. You picked Yotsuba? You picked Yotsuba. Damn, you just finding that out. You picked Yotsuba.
I don't remember.
All of them wanted him, bro. You picked Yotsuba.
Yosma doesn't even like him that much.
She does. She just doesn't like show. Like, she doesn't like.
I don't know, but Yosma like mid, you know? It's like
She is mid. What are you talking about? Like, I hated it. She was like one of my least favorites.
yeah.
Literally, like,
She didn't have character.
her or Ichika. Like, her and Ichika, as long as you didn't pick any of those two, I would have been chill if you fucking picked Yotsuba.
还有妈，阿姐姐，
Omelet with tuna and cheese. I'm low key, I might go get
I'm hungry too bad. Nhớ đi ăn được,
Spinach.
nhớ đi ăn được.
Yeah, egg white, spinach, cheese, tuna. Yeah.
Yeah, it's good, but the pan, I'm watching it. I don't want to cook.
You need to watch
Shit, see, if we still have the chicken. If we
Oh,
still, there's still feed, burrito and feed.
Or like we already bought it, might be something.
So just be like, oh, I'm gonna get
What's our pasta?
uh, I have to go to the gym.
It's from this movie, right?
Yeah.
You know,
Are you doing those stuff? With me.
no, you wake me up.
Wait, me up
Oh, the earliest one up.
there you
No, mày có biết dạo gần đây ta muốn hay là
go.
buồn?
Me too.
Tao không dậy được luôn á.
Me too,
Tao
bro.
không. You know why? Because we're all up with time.
I sleep at like
Bro, I
5,
just
bro.
did fucking more stats.
I woke up at 7.
Đi ngủ.
You done?
Xong rồi.
You were doing stats as you're calling your friend.
Yes.
You really able to focus.
No.
Wait, what's that?
Mấy cái distribution, mấy cái standard deviation, hypothesis testing ấy,
Are they gonna make you do R?
some probability ấy,
Are they
R
gonna
thì
make you do
cấp phí á. Thì test á.
R is a coding software.
Yeah, but
No.
they make you they make you use it.
No. Cái này.
I would argue that if you're gonna study finance, they're gonna make you study the shit out of finance stuff.
Thì cái course này là Excel course mà.
And you're gonna take on.
Yo, you can't let those prey go to waste. Cable punch.
We call them pressures.
It's fine.
I'm so under though.
That's really
I'm so
calm hả đấy? Tại, because we keep waking up after you
I'm high key on like 1,000 calories.
See that?
That's not healthy.
Eat good.
That's not fucking healthy. It might not even be 1,000.
Think too much. Gotta just eat.
I didn't try to he didn't try to he's not trying to see us move.
Hell no. I would eat, bro. There's so
See, like the chicken breast would have been there.
Wait, oh yeah, there's Shin Ramen light.
Okay, that's just like
Zero
See,
sorry.
now he's actually
3 grams of fat, 70 grams of carbs.
Yeah, and how many grams of sodium?
I don't know about sodium. I don't track sodium.
sodium just want to make sure your face is bloated.
That's it though.
But like you don't want that.
That's not fat. So like it's good for you.
I'll
Bro, Shin Ramen's better than all that pasta and full pasta. I'm ready to go. Yeah.
Figure it out.
Okay, let's just thug it out.
So you're gonna go to sleep, guys?
Yeah.
I'll probably go.
Thug it out.
I'm ready to eat.
Do you wanna stop that if I do?
But my butt needs to grow.
Huh?
My butt needs to grow.
That's exactly what the fuck I'm doing.
That was the only deal we had.
Should we go escape and buy like 2 protein shakes or something?
I eat Greek yogurt.
You had Greek yogurt the whole time?
I only have one pack. Should have eaten it.
Wait, can I get one?
You get one pack, boy.
Oh, like that's just I thought you had like a pack. Oh, that's not even eating, you're drinking that shit.
Milk.
You gotta eat that thing.
Wow.
Holy shit. Rice had 60 grams of protein for 300 calories. No, I just eat egg whites. No, 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 no. It just tastes like tastes like rubber. It tastes like white rubber. It comes in like a carton. Uh-huh.
I haven't done bullshit. Alright, I watched both of these. It's either I watch these, and then tomorrow I watch these, and then I go to school and then I finish the 2020. Yes, I agree.
Two issues that
Yes, I agree. Do I have to take another monster? Maybe in the upcoming weeks, but right now I'm okay.
we'd like to have a look at in this lecture. First of all, the idea of a cumulative distribution function, which is very closely connected with that of a probability density function. And then we'll move on to the most famous of all continuous random variables, which is two functions are split or cat, and so here to the right. Whether this is a 1620, extract which of the two.
Nice. Whoa, we're 3 away, boys. We're 3 away. Wait. Locked in. That just gave me a sliver of hope. Standard normal distribution. Without doubt, the most important probability density function we encounter in the real world is the standard normal distribution z tilde n0 1. The normal distribution has the following beautifully balanced and elegant look. Alrighty. When we say z tilde n0 1, we are saying that z is normally distributed with a mean of 0 and a variance of 1. The other ones are n and p, which is for binomial distribution it's n and p, right? And then we've learned about the probability density function and the cumulative density function, which are kind of derivatives of each other. The binomial distribution is made up of the binomial coefficients and the yeses and the nos, right? Probability and the shots, okay. Whereas this one is mean and variance. You'll see in year 2 that almost all statistical issues and questions eventually find their way back to the normal distribution. Sums and averages of all populations look more normal as the size of the population increases. Wow, mathematics is beautiful. Guess I do continue to take math and accounting.
Now to what is really the most important probability density function, which is called the standard normal distribution.
I'm learning this at 3 a.m.
And here's a picture of that particular PDF. And it turns out that if you look at any population, so say you're interested in the height of
it is a probability density function.
Individuals, the weight.
So what does it look like if I
really
integrate?
Almost any random variable, time intervals, they do tend to eventually follow
Could
a
I
standard
integrate the
distribution.
normal
You
distribution?
usually have the bulk of the people in the middle. So most people are average.
Oh
You
yeah.
have people
Sorry.
up in one end, up in one tail, and a small number of people down in the other tail.
Because it's e to the minus x squared, which is not integrable.
Now, we can prove that
Tragically, the actual equation of the normal curve is horrendous. Funny.
sums and averages eventually will follow a standard normal distribution, regardless of what the actual
I want to make some
quantity of
cash in
interest
poker.
is. Now, this particular PDF is N01. That is the mean, and that is the variance. So it's a normal curve with a mean of 0 and a variance of 1. If the variance was less than 1, it would just be a little bit more peaked. So by varying the variance, or changing the variance, you can sort of stretch it out horizontally or squash it up horizontally a little bit. We usually denote the standard normal distribution by a capital Z. So Z is distributed in 0, 1. So when you see this statement, you read that as
Z
the
is
random
normally
variable Z, the continuous random variable Z, is distributed normally with a mean of 0
distributed
variance of 1.
normally with a mean of 0 and variance of 1.
Now, the nice thing,
Distributed.
there's a few nice things about the normal distribution, but there's also a few really, really nasty things. The nice thing is it has a nice balance. It's often referred to as the bell-shaped curve.
Mm.
It has an axis of symmetry, so it's symmetric about Z equals 0.
You mean
And
Z equal,
it just generally has a nice balance and look to it. The trouble with it, the problem with it, is that its equation is incredibly complicated.
1 to the... So, I mean, it has the e to the minus 2 x squared on it. And the 1 over square root of 2 pi is... Ooh.
So the actual equation of the normal curve is essentially e to the minus
So there's a
x
normal
squared,
table of probabilities.
or if you like, 1 over e to the x squared. Now, what is a little bit remarkable about that equation is that you can't integrate it. That's a function that we actually can't integrate. And what that means is if you want to start extracting probabilities from the standard normal PDF, if you want to start pulling probabilities out of this, you can't use calculus for the simple reason
You can't
that
integrate.
the actual integrals that you want to do cannot be done. Now, you may wonder, well, why don't we just go somewhere else? If we can't integrate this PDF, why don't we use some other one? But the reality is that this PDF sits at the center of probability and
Milan Power is the
statistics.
GOAT.
There is nowhere else to go. You have to use this thing. Now, what we do instead, because the calculus fails us, well, there's choices now. In the old days, we used to use tables. Nowadays, you can actually just get an app or a piece of software which will evaluate these numbers for you. The table that we use actually gives us the cumulative distribution function. So when we look something up in the table, we say phi of z, and what that calculates for us is the probability that the standard normal random variable is less than that particular value. Let's just have a quick look at the table. Now, in the future, you may be using the table. There are various, unfortunately, different types of tables floating around as well. Or you may just be using a computer, or you may go to the web. But if we just look at the table, I've included the table in this lecture and also in the next lecture, just as the very last page of the lecture. So what this table gives us, if we think about the standard normal random variable, always has that look about it. It calculates the area to the left of that value. Now, what that means, for example, if you look up 0, you get a half, which makes sense, doesn't it? So what that means, if you find the area to the left of 0, that is a half, because it's a half the total area.
Okay.
You will observe.
It
Now,
only
let's
goes to
first of all talk
minus
about how
3
you look
and
up a
3.
number. So say you want to look up 1.89. Let's
So you scroll down to 1.8, and then you go to 1.89. So it's bottom right here, maybe?
say you want to look that number up. You go to 1.8, and then you skip across to the 9 column, which is the last column,
Okay.
and that's 0.9706. So there's 1.89. We would refer to that as phi 1.89. Now, what that means in terms of a picture is that if you go to
If I have some z at 1.89, That means the probability that it's going to be less than or equal to 1.89 is 0.97. So it's very, very left. It accumulates almost everything. Oh.
0.9706. So the area to the left of 1.89 is 0.9706. In other words, it's almost the total area. Now you can see that when you get right up the top, 2.99, you've almost picked up all the area. So by the time you're at 3, by the time you've hit 3 on the right, you've picked up almost the entire area underneath the standard normal curve.
Okay.
On the other hand, if you go to the other end, so if we go to -3, get rid of all these. So if we go to -2.99, you can see that there's almost no value there. It's almost 0, because in terms of the picture, -2.99 is around about there. There's almost no area to the left. Now, admittedly, this table is a bit clumsy, and in the old days, it's all we had. So before we had handheld computers, really the table was the thing to be used. But nowadays, of course, you can just look these things up as well. Different tables will look a little bit different. Some tables don't have the negatives at all. They only have the positives. Different bits of software will calculate these probabilities a little bit differently. But anyway, that's the standard normal table. It looks to the left of a point. It is a cumulative distribution table. It calculates for you the area to the left of the point that you're looking up. This is the first decimal place here, and by skipping across, you pick up the second decimal place. What if you've got more than 2 decimal places? Well, then you need a better table. So this table only goes to 2 decimal places. Okay, let's have a look at how we actually use the table to calculate probabilities. So just a couple of things. So when you look it up, when you look these up on the table, that's what it looks like. So we call this phi of z. So that's just a capital phi there. And it measures the area underneath the standard normal curve to the left of that particular point. We only go to 2 decimal places. You can go further if you need, but the table only goes to 2. And the table always looks left. Do be a little bit careful that that you're aware of what sort of information will be supplied to you in any paper that you might be sitting. So some exams might just have a table. Some of them might let you look things up on your phone. So before you do any exam involving standard normal random variables, just clarify from the examiner exactly how you're meant to look these things up. Certainly you're not going to memorize the table. And they are not things you can calculate. So these are not things you can do by hand. You need some sort of help. And different exams will have different ways of actually calculating these probabilities. Now let's have a look at how we use this table. It's very, very easy. So suppose that Z is distributed n01. Z is a random variable. It's normal. Now what normal means, of course, is it has that lovely shape. And we're telling you that the mean is 0 and the variance is 1. So it has a mean of 0, variance of 1. If you increase the variance, it sort of stretches it out a little bit. And of course, if you change the mean, we'll talk a little bit more about this later on. If you change the mean, it essentially picks it up and puts it somewhere else. We'll deal with that in the next lecture. In this lecture, we're just going to have a look at n01. That's all we're going to deal with. And we'll discuss in the next lecture exactly how you go about dealing with more general types of situations. Now this first problem here, this is quite literally phi of 0.79.
So you just go to that table.
0.79. Remember that the table always looks left.
So
Now,
he's gonna scroll down to the table.
0.79.
We're just trying to look at it.
Find it.
0.79. we're gonna scroll, and we see that 0.78 as 7852. So that's the probability of the Z being normally distributed at 0 with a variance of 1. That's the probability.
0.7 is there. We go all the way to the right hand end, 0.7852.
Yeah, that's it.
So 0.7852.
And I'm assuming that the probability of Z being at 0.79 exactly, once again, is 0. And PZ less than 0.79 is the same as 0.878952.
And that's all there is to it. So there's not much to it.
Yep.
Just in terms of the picture, get a bit of a feeling for what's being said here. Standard normal curve. We're positioning ourselves at 0.79.
Yep.
And that area is what we've calculated.
Yep.
We've calculated the area to the left of that point.
Yep.
Now, this is always a problem, isn't it? What is the probability that Z equals 0.79? That is most definitely
Not
0.
Not.
Any continuous random variable has a 0 probability of taking on one of its values. So be very much aware that the table doesn't look at 0.79. It definitely looks to the left of 0.79. The probability that Z equals 0.79 is 0. And of course, what that means is if you want to make the inequality strict, it doesn't really affect things at all. That will also be a point.
Larger than 2.47. Once again, left looking, we're going to do 1 minus that one, 2.47.
So this is 1 minus phi.
Yep.
Of 2.47.
Yep. Is there anything else? E is also phi of minus 1.24. Maybe F? Well, F, we have to do it the other way, which is phi of 2.41 minus phi of 1.71.
This is 1 minus. So we're now looking up 2.47 in the table. So 2.47.
2.47, is that right? 2.987, 0.9932.
2.4 is there. 1, 2, 3, 4, 5, 6, 7. 0.9931.
No, he got it wrong. 32. Come on, bro.
31.
Come on, bro.
Which is 0.0069. Not much.
You tried.
68. 0.9931. So I just go to the wrong table. 2.47. Let me just check that again. 2.4. 2.4. 1, 2, 3, 4, 5, 6. It's a bit hard if you haven't got a piece of paper here. So 7 columns to the left there. 0.9932. Yep, need to go an extra one, didn't I? So 0.9932.
Don't worry, my goat. You're still my goat. You're still my goat.
That's an 8. Lovely.
Lovely.
Now, just in terms of a picture here, again, just make sure.
That means it's like super far right. How do we do this? So this is phi 0.79, which is equal to 0.7852. 0, 0.7852, 1 minus p probability that z is less than 2.47, which is the same as phi 2.47, which is equal to 1 minus 0.99 32, which is equal to 0.0068. And on the graph, it would look something like, sorry, we'll put that right there. This is 2, 4, 7, and then it's right at that corner. Maybe I do red. Zero 0.0068 or 0.68%.
Sure that these numbers make some degree of sense to her. 2.47 is way to the right, isn't it? And we're talking about the probability that Z is bigger than that value. There's not much area there. So it's not surprising here that we get such a small number, because indeed there is not much area there. Negative 1.24.
Wow, my hands are
Now,
hurting.
just be a little bit careful here. This is just phi of negative 1.24.
Yep.
Some tables don't have negatives. Our table does. So negative 1.24, negative
but if it
1.2
was,
is there.
If it was 1.24, let's think. If you were sitting at 1.24, you would take 1 minus 1.24, phi 1.24, and then you'd get the right hand side, which is equal. If you mirror it, it's gonna be the left hand side. Right, so 2.4 goes right here. Let's scroll. 1 point. Yep. 1.2. Negative 1.24. Which is also 1.24. Where's 1.24? But 1 phi of minus 1.24 is equal 1 minus phi of 1.24. 1 point. $1075, which is exactly seen as above.
That's 0. I forgot that first one was 0 before. It is 0, isn't it? So that's 0, 1, 2, 3, 4. There it is. So that's 0.1075.
And then this last one is
Now, when it comes to a question like F, you just have to be a little bit careful. In terms of a picture, we're just going to...
I got you. You don't need to look at him. Even though he's taught me everything. It would be... It would be like this, subtracting this, oh sorry, to get us this.
You have to use this table in an intelligent way. So this is 1.71 and this is 2.41, and we're just after that little chunk of area there. Now we can't do this directly, but what I can argue is that this is phi of 2.41 minus phi of 1.71. In other words, we go to the left of 2.41 and we subtract away the area to the left of 1.71. Now, if you just sit down and think about that for a second, you'll see that if you go to the left of 2.41 and then take away whatever to the left of 1.71, you will be left with that little banded area there. And this is the way we calculate the probability that Z is between two limits. Now, as usual, you may be wondering, well, why aren't we just integrating? Why don't we just integrate
Can't integrate it,
between
bruv.
two limits like
Come
we
on,
did
man.
before? And the answer, it'd be lovely if we could do that, but the answer is we can't do the integral. The integral is too hard. We have to do something else. So to finish off here, 2.41, again to the table,
I want poker chips. I've got 50-cent
2.4,
coins. Thanks, Sean, for
that's
letting me use these.
4041, put 9920.
I
You can
have
see
my
it's
poker chips
clumsy.
soon.
And 1.71,
Keeps my hands busy.
1.701, 0.9564. Backwards, which
We need to be able to use the table backwards, looking up probabilities in the main to produce z-scores. Oh, some alpha such that it's equal to 0.9. So find an alpha such that RZ, so find alpha such that this is equal to 0.9. Let's go for it. Well, we're looking at 8413, 843, 861, 85, 86, 88, 86. We're getting close to this one. This one is closer, right? This one specifically is the closest, right? It's a thousandth of a point away, and that is 1.28. Here you go. 0.01. 0.01. 0.1. So we need 0.01. So we're getting close to here, to here, to here, to here, right here. Once again, we're getting close. This one is closer to 0.01. Closest to 0.01. So alpha is minus 2.33. Oh, sorry. It says something that's larger than alpha. So we want 1 minus alpha is equal to could check with the negative value and mirror over. I gotta write that better. We could check alpha phi of alpha closest to 0.1 is some value alpha, but we could mirror over to get some z larger than alpha. Phi of this is equal to, and phi of 2.33 is equal to 0.991. No, 1. 2.33 0.123 901. Some z less than alpha is this, left to right. 0.07 0.0735 0.07 567 0.5 0.735 minus 1.45.
Becomes even more difficult. So that let's this region, yeah, 1 minus the probability that z is less than alpha is 0.01, and 0.99 is equal to the probability that z is less than alpha. So just dragging everything from one side to the other, probability that z is less than alpha has to be
Okay.
0.99. Now what that means, of course, is we need to go to the table and pick off 0.99. Now that's going to, of course, is we need to
Okay,
probably
sure, you can do that. Or transfer to left looking, right? P z is equal to 0.01. So 1 minus P of Z is equal to 1 minus 0.01 is equal to 0.99. So P of Z sum alpha is 0 to 0.99. Then alpha is equal to 2.33.
The Z is less because 1%. Now that of alpha, probably the again, we just negative the 10 need to be forwards.
What if our normal distribution has different mean or variance? How do we calculate probabilities? Well, you can scale it, right? We have learned that. You scale it by whatever the table is, no? If Z was distributed normally with a mean of, I don't know, 5 and a variance of 2, then if we want to calculate the probability of Z being less than, I don't know, give me alpha 0.9, we can start with finding alpha is equal to, then by Z being normally distributed at 0 and 1, alpha is equal to what was the given number for phi? What is it? 1.28. Then mu plus alpha is equal to 6.28. And var I don't know, var Z is equal to, something like that. That's my guess.
Backwards. The end of the lecture, 735, and that's negative. Regions are. So it's not just a question of just producing numbers. You do need to be aware of exactly which bit of the standard normal curve you're picking off, and whether you're finding phi of alpha or whether you're finding an alpha which has a particular phi, whether you're using the table forwards or backwards. Now that brings us to the end of the lecture. I think a couple of things are immediately obvious that we're going to have to do. What if I had a normal distribution which was centered around 400? Which is perfectly possible, of course. It's in fact quite rare for a normal distribution to be centered around the origin. For example, if you were analyzing marks in an exam, usually they'll be centered around maybe 70%. They're certainly not going to be centered around O, hopefully. So we need to be able to move these distributions around a bit. And what we'll have a look at in the next lecture is not N01, but rather N mu sigma squared. In other words, I'm going to allow myself the possibility of having a random mean and a random variance. Now you may think, well, does that mean I'm going to have to produce 1,000 different tables? And the answer is no, that we have a nice little trick, which is just a property of the normal curve really, which enables us to put ourselves into a position where we only ever need one table. We only ever really need the standard normal. But once again, if you use computers to do this, the computers will also do it for you. quite nicely. Okay, so the last lecture, we'll have a look at mu sigma squared, and also interestingly the connection between the normal distribution and the binomial distribution. And we can use the normal distribution to approximate the binomial distribution. And we'll have
people are
those
losing
issues.
because they can't do this. I'm gonna sit through this shit. Because I'm gonna stay focused. I'm gonna drink another piece of caffeine shot. I have not drinking my creatine today.
You will recall in the previous lecture that we had a look at the standard normal random variable. And that was the random variable with the classic bell-shaped structure, Z, distributed normally with a mean of 0 and a variance of 1. Now, this...
Wait, that's sick. I need to stare at this until it makes sense. X is a... Sorry, I'm gonna... X is a random, continuous random variable distributed normally at mu, which is our mean, and sigma squared, which is our variance. But this also implies that our x as the random continuous variable, subtracting from mu, once again we see that distance and we divide it by our standard deviation, that becomes a object that we can once again basically factor out and distribute over the normal distribution at mean 0 and variance 1. That's very cool. If a discrete random variable x follows a binomial distribution with n trials and a probability of success of p, then x can also be approximated by the continuous random variable y. Where the hell do you get y? Oh, okay. Whoa! NP is the... okay. If a discrete random variable follows a binomial distribution, then it could also be approximated by the continuous random variable. Whoa! So it's really connected. Okay. Very cool. Play on, brother.
Random variable is balanced about the vertical axis. The mean is 0. And having a variance of 1 simply gives you a measure of spread. If the variance rose from 1, say the variance was 100, it would be more stretched out.
Valid.
So you have a more stretched out sort of object.
Valid.
Now, although in the previous lecture we were able to answer all sorts of questions regarding Z, there is a problem, of course, and that is that most of the time the mean will not be 0 and the variance will not be 1. So, for example, if you're trying to analyze exam marks, you'd be expecting this sort of structure where maybe that's 70%. So you certainly would not be expecting there that the mean would be 0. So the question then is, well, how do we deal with these other random variables? How do we deal with the normal distribution where the mean is not 0 and the variance is not 1? And it turns out that it's actually surprisingly easy. We certainly do not need thousands and thousands of tables. One table will do the job. So we have only one normal distribution.
This is so sick. But Milan Pohor has a beautiful, beautiful way of teaching it. So that becomes our whole object, is what I'm assuming. And then if we have alpha, okay, right, then if P of is less than 35, this is alpha. Usually when we're given the alpha, we just bring that alpha into the thingy, but if we have 35 minus 30 over 9, what how much is 5 over 9? 5 what's 50 over 90? I can't split it up, bro. Come on. 10 over 18 is what? Can't do it. Zero 0.555. Does that mean that I can now go to 0.55? 0, 1, 2, 3, 0, 1, 2, 3, 4, 5. 0.788. So 0.7088. Is that how Mr. Milan Pahor would Milan Pahor?
Of course. Now, you may think, well, I just look up 35 in the table, but you can't look up 35 in the table. If we go to our standard normal table, of course, it only runs, where is it? Way at the back here. It only runs from -3 up to +3. It certainly doesn't stretch all the way down to 35. Now, we have a little trick here that will bring us back to a situation where we can use the standard normal random variable. So we just have a little
fun,
a little trick, which will actually take us back to a situation that you will be familiar with from the last lecture. And let me just present the fact and then we'll use it. If X is distributed normally with a mean of mu and a variance of sigma squared, and please observe, I'm not using Z there. We really do restrict Z to be the standard normal random variable.
okay?
So X is distributed normally with a mean of mu and a variance of sigma squared. If you subtract the mean and divide by the standard deviation, not the variance, the standard deviation, you will produce an N01 random variable. So to get from a general distribution to a standard normal distribution, all you have to do is subtract the mean, divide by the standard deviation. And that will do the job. Now, you will remember, let me just prove this, or at least half prove this. You will remember from earlier in the course, expectation is linear. E of ax plus b is a e of x plus b. And variance is very strange, isn't it? Variance of ax plus b was a squared times the variance of x. Let's have a look at the expected value of x minus mu on sigma. The 1 over sigma comes out because of the linearity, and this becomes expected value of x minus the expected value of mu. And this is then 1 over sigma mu minus mu, which is 0. So you can see that this random variable does indeed have an expected value of 0. Also, the variance of x minus mu on sigma, you will remember that sliding a variable along has no impact on the variance. So pushing a variable 10 units up the axis will not impact on the variance because the spread of the data has not changed. The mean has certainly changed, but not the spread. So we can just kind of scratch that out. And you'll also remember that the 1 over sigma pulls out as a square. So we end up with a 1 over sigma squared out the front. So we end up with sigma squared on sigma squared, which is 1. So what that proves for us is that this random variable has a variance of 1, which is essentially what we're claiming. And in your lecture notes, in your printed lecture notes, you'll also find a proof that it is still normal in shape. It still has the same shape. So what that means is if you begin with n mu sigma squared, you can get over to n naught 1 simply by subtracting the mean and dividing by the standard deviation. That's all you have to do. Now this turns out into something quite interesting. So if you want the probability that x is less than or equal to 35, and this was our problem up here, wasn't it? We can see that the answer should be a little bit more than a half. What do we do? This is the probability that x minus 30 on 3 is less than or equal to
On 3?
35 minus
yeah.
30 on 3.
Oh.
And
the probability that x is less than or equal to 35 is the same as, so we're going to substitute subs x minus mu over standard deviation this is also 35 minus mu over standard deviation is equal to the probability of x minus 30 over 3 is less than or equal to 5 on 3, which is equal to probability of phenomenal.
Takes a little bit of getting used to, but really all I'm doing here is I'm subtracting the mean, I'm dividing by the standard deviation, not the variance, the standard deviation. And I'm doing that to both sides of the inequality. Now this becomes the probability that Z is less than or equal to 5 on 3. And what I'm claiming there is exactly what I proved for you just above, that this random variable becomes the Z random variable. It turns into something with a mean of 0 and a variance of 1. And you can see that all the numbers have been brought back into range. So suddenly we're looking at this value, probability Z less than or equal to 5 on 3. This is a phi of approximately 1 2/3, 1.67 to 2 decimal places. So just rounding up there, isn't it? It's 1.66, but I'm rounding up to 1.67. Now, 1.67, you'll remember we can look up in the table. I'm now in a position where I can look it up in the table, a long way down the track. So 1.6, where is it? There. That's 0, 1, 2, 3, 4, 5, 6, 7. 0.9525. So, quite a long lecture, this one. And this is equal to 0.9525. And of course, that is coming directly from the table. Now, if you're using software, it'll come from the software. And I must admit, if you have software which is sophisticated enough, you probably won't even have to do this. You can probably just enter in the mean and the variance. But it is important to be able to understand what's going on behind the scenes. Okay, so it looks as though we can always get back to the standard normal. And it's just a question of getting used to that process. What's the number one error we see? People divide not by the standard deviation, they divide by the variance. We will give you the variance, usually, but you need to divide by the standard deviation. Okay, let's have a little example. We'll draw a picture for each of these just to get a feeling for what's going on. I said before something a little bit bigger than a half. In fact, it was much bigger than a half, wasn't it? I suppose that's a consequence of my diagram. So maybe the 35 should have been further across here a little bit. It's always hard to see from these diagrams what's going on. The table does that heavy lifting for you. Okay, so what have we got here? X is distributed normally with a mean of 70 and a variance of 16. So it'll look something like this, where that is 70. Variance of 16 means that it is stretched horizontally a little bit more than normal.
Friday, let's do some math. So It's okay. Just wait a few days.
So it'll be a little bit, the variance will be larger. There'll be more and more data further and further away from the mean. You want the probability that x is less than or equal to 78.
No, I'm supposed to do the question. What am I checking? Okay. Right. Mu is equal to 70. Sigma squared is 16, so sigma is plus or minus 4. But we'll just make sure that it's 4. Then px minus 70 over 4 less than or equal to 8 over 4 is equal to z less than 2, which is equal to, well, 2 dot dot 0.9772. X minus 70 over 4 is less than minus 2 over 4. Pz less than a half is equal to 0.385. Is that what I saw? 3085. It's larger than, so it's 1 minus p of x 60, which is equal to x minus 70 over 4 is less than minus 10 over 4 is less than pz of, what's that? 5 on 2 is minus 2.5. One minus z less than minus 2.5. Less than 0.0062. 0.62. 0.9. 938. Which, I mean, if we're looking, if this is 70 and you've got one standard deviation, you got 2 standard deviations, you got 3 standard deviations. Each standard deviation is with 4. And this one is more than 60, right? So it's like right here, 60. Let me do this. This one is less than 68. 68 is like right here. And this is 1 standard deviation away. This is less than. Right. It should be less than half. It's kind of in the zone. P x minus 70 over 4 5 on 4 66 minus 70 is minus 1. PZ 5 on 4 minus PZ less than 1. Did I just see 1.5, 5.4, 5 on 4 is 1.2. 0.8849. And was it minus 1? 0.1587. So 0.8849, 1587. 8849, 1587. Okay, then we have 0.7262, which would be like 66, 75. Which looks like it takes up the majority. Okay. Finding. So this is at, okay, suppose that x is that, find the value of alpha of x exceeded by only 10% of the population. So firstly, we'll do x minus mu over 6 so z. Okay, we start off with this. Then find p of x find the value of alpha of x exceeded by only 10%. Is larger than some alpha is equal to 0.1. Then one minus p of x less than alpha (0.1) p x less than alpha is equal to 0.9. px minus 20 over 6 is less than alpha minus 20 over 6 pz alpha minus 20 over 6 is 0.9. Now I find 0.9 on this table. This one's close to 0.9, right? 1.28. Alpha minus 20 over 6 is equal to 1.28. Alpha minus 20 is equal to 6 times 1.28 plus 20 is 6 times 1.28 times plus 20. So I get 6 plus 20 plus 0.28 times 6, which is equal to 1.2 plus 0.48, which is 1.68 plus 26, which is 27.68. Ah, nice.
So where is 78? About there. You want
Nice.
I won't say a little bit less
Cooked
than a half.
it.
No, it's probably going to be a lot less than, sorry, a little bit more than a half. It's probably going to be a lot more than a half.
Oh, you guys didn't see
So
shit.
it's certainly a half plus a significant chunk. So what do we argue here? This is the probability that x minus 70 over 4 is less than or equal minus the probability. Exactly the same thing to...
Do we get the answers right? Fuck. Wait, no, it's this one, eh? 9972 or 9779? I don't know, man.
all the random variables
2, right?
is less than variance of 16. Standard we do it on sigma into 4. I have the 4 deadline 1.2 variable. Please remember, no matter again, 977. 0.9.
0.977. My bad. That's my fault. Zero 0.9772. Typo. Misread. Okay.
977. Will you work here? The is array. Yeah, it's pretty much. So this is the probability that x minus and z. So just looking it up in the table. So this is a 70. This one is. This is. And what's happening in the table?
1 minus that. Oh, minus 2.5. Yep. So same as what he wrote. Here he's writing something phi of minus a half, phi of 1 minus 2.5, which is what we also have. This 1 minus okay, I guess we could write 1 minus phi of minus 2.5, which is the same. And here as well, which is phi of 0. Minus a half. Okay, so we're chill.
Table and give yourself an answer. 20.
1 and 1.25. Jeez, what the fuck? Wouldn't it be this bigger one? Yeah, wouldn't it be like 75 minus 70 over 4 here? Okay, I know, I'm just gonna...
-1 minus the probability.
Is that right? Ah, not 1.2, it's 1.25 minus, so phi 1.25 minus phi 1.
Okay, variable
Okay,
of
that's
the
fine.
from the full trick and derivative variable.
This we know how to
You
do.
get 20,
We just
and this
finished.
is often referred to of x. The pivot plays z program. Okay, now often, particularly in examinations, you get questions which are just words.
Oh yeah, let's do this. Let's do this. Oh yeah, I have to one sec, I have to finish my COM 1100 homework. Like right this instant. Where's chat? Chat. Help. Test your understanding. Why the fuck would I give a shit? What's on your mind today? Let me know how we can start. We need that in our Notion, by the way. One sec. One sec, one sec. I don't want chat fucking... I'm wasting my money and my time learning about chat when I could... Honestly, I don't know why. You know, with school and shit, and you've got like an environment. Like, if you stuck me with the best like econ people in the world, at least I'd be making money for myself, you know? Not like bankers. Or do the bankers make a lot of money? Có đêm anh mơ giấc mơ một hạnh phúc. Oh yeah. stat. Hell yeah, I'm gonna study statistics and information systems. Comp science. Yeah, and I get to continue my math course, which is fucking great. And accounting is, oh, hell yeah. Infosys. I have more than enough kind of ground to go crazy on numbers and Infosys. Statistical modeling computing. And I get to have some nice electives like marketing 3085. Yes. Cooked it. HD'd it. I'm so tired. Wait, why have they never talked about this? No way. No way, really? That's crazy. Yeah, I do. I think I want to build a $1 billion e-commerce company. Yes, I can do it. A $1 billion e-commerce company. Wait, that sounds so interesting. Oh, this is like a NBA. I'm so tired.
and it's your job to actually somehow convert it into mathematics. So
Can we finish this? Suppose that the time taken to be served at a particular bank is normally distributed with a mean of 15 minutes away. So time, let's do x. Let x be time served at bank. And we have that x is normally distributed with a mean of 15 and a variance of 4. So mu is equal to 15 and is equal to 2. Okay, find the probability that the individual is served in less than 12 minutes. Okay, A, P of x less than 12 is equal to P of x minus 15 on 2 is less than 12 minus 15 on 2 is equal to z less than minus 3 on 2, which is equal to phi of minus 3 on 2. And that is equal to minus 1.5. 0.0668. 0.0668. B between 14 and 17 mins is P 14 x 17 is equal to P x Px less than 17 minus Px less than 14 is P of x minus 14, was it? Sorry, 15 over 2. 2 over 2 minus P 15 over 2 minus less than minus a half, which is equal to 1 minus a half, which is pi. One, right? 0.8413 minus a half. Minus a half. 0.3085. Thirteen, 8, 0, 10, 2, 3, 3, 5. 0.5328. Find the quickest 1% of serving times. Quickest 1% of time served by P Z less than alpha is equal to 0.01. P is x minus 15 on 2 is less than alpha minus 15 on 2 is equal to 0.001. P is z is less than alpha minus 15 on 2 is equal to 0.01. We have at 0.01, we have zero point zero 0.01. Minus 2.33. So alpha uh, 0.688, 5328, and 10.34 mins. Normal approximation to distribution. Maybe that is tomorrow.
Example 3 deviation. This balance 15 on 2 meters, so very complicated minutes. Normal distribution into play in order to eventually.
Okay, we have got one more lecture that I can try to get done at like 11 when I wake up. Very tired. Good night, guys. I am